Hey everyone and welcome back to the channel. In the last video we talked about cyclic sort and we talked about few cases. We discussed about the time complexity and all, and in this video we'll be starting with we'll be doing some questions related to searching and sorting both. I wanted to cover a big some few questions, medium and hard level, some easy medium and hard level questions from Leetcode to make sure the concept goes clear in all your minds. Basically wanting to develop the logic about all the types of searches there are in this. Alright, so we'll be starting with searching questions first. So yeah, this one's search in rotated array part 2. Basically let's talk about that. So what I know we discussed about the rotated sorted array, but this one consists of duplicates. We didn't discuss that case, right? So let's start with that one. All right, so we are given a if you remember in rotated array we would be given something like 3 4 5 6, and it is sorted, but the last part of the array will be shifted to the first. So instead of 7 and 8 in the end, we will be writing that over here, right? So here these last two elements have been shifted to the first part of the array. So it is sorted, but it's rotated 2 times. Similarly, when we talk about duplicates, it's nothing else. It's just consists of some duplicates. Let's say 7 7 8 3 5 5 6. Yeah, this is an example of rotated sorted array, right? So basically we are asked in the question, we don't even have to find the target, we don't need to return the index, we just have to return true or false whether the target is in the array or not, right? So let's say our target could be something like 6 or maybe 7. Target doesn't matter that it is a duplicate or not, right? 7 is a duplicate but 6 is not. We just need to return true if at least one element of that target is inside the array. Alright, so if you remember the 4 cases for this one, we were talking about the first 2 were related to mid. We know that when we talk about mid, this is a start, this is end, and this could be our mid in the first case. When we talked about mid, we knew that in rotated array, the element before it, there will always be one element before the mid element that will be greater. The remaining part will be in ascending order. So here is that point. We know that the pivot element is this. This element will always be greater than the element after it. That will only be the case for that, right? So 8 is greater than 3, but for 7, 8 is greater than 7, right? That is the case. But 3 is not greater than 8, meaning, sorry, my bad. 3 is not greater than 8. So only once the case occurs where the mid element we find every time, the element before it will be greater than it. And if that is the case, then we know that that element is our peak element. And we simply, then apply the binary search from those ranges, because we find 2 parts. Basically, it's simple. We just need to apply binary search from 2 ranges, 2 parts of the array. One will be this and one will be this. Basically, what we are trying to do in rotated arrays every time is we are trying to find 2 parts. And basically, where those 2 parts occur is dependent on mid element, means the pivot element. When we find the pivot element, we know that all the elements till the pivot will be in ascending order, means the first part we found is in ascending order, and the second part after the pivot element will also be in ascending order. Then we simply apply the binary search in those 2 ranges. That part remains same. So in first and second cases for original rotated array, we would talk something like if the mid element is less than its previous element, likewise also we would check that to compare it with the previous element, we would also check if mid is in the range, meaning mid is greater than the start, because we are comparing one element before it. So if mid is the start, then we can't compare mid minus 1, right? We need to always check the boundary cases as well. So this is just for the sake of boundary casing. So if that is the case, and we know that this element is greater, then we know that it is our pivot element. So we would return that index as our peak. Similarly, we would check from the end. So for that, we would check that if the mid element is greater than the element after it, means mid plus 1, right? And alongside, we would also check that mid is in the range, meaning mid is not the end, because if we are checking the element after it, and if mid is the end, then we would get out of bounds exception. So we would also keep a boundary check that it is in the array and the end is not the mid. In that case, we would simply return mid, because we know that there will always be one element that will be greater than its next. Alright, so we would return mid. Alright, now if you can see that these two cases would also apply for duplicates, because we are simply checking within the range of the array. We are not yet changing the ranges of start and end. We are not changing the positions of start and end. So it's okay, it's perfectly logical to apply those two cases again in the start and end ranges, right? It doesn't matter. What happens when we come across a situation where duplicates? Let's talk about a case. Let me write the case so it will be clearer. Let's say our array could be something like 5 elements and 2, 5, 2, 2, 2, and our target could be something like 5, right? Now here we will be checking our mid element with the element before it and after it, right? That all is correct. So 0, this is the end, so this is our start, end, and this could be our mid. Now for the other two cases, we would check that if mid is greater than start or mid is less than end or something like that, right? We would use to check those for the third and fourth, right? We would check that. But here, if we apply those conditions for the non-duplicate rotated array, where we would be checking that if the mid element is greater than start, or it's something, or if we are comparing these two, mid and end element, then we would come across a situation where mid element is equals to the start element, which is also equals to the end element. Yeah, in the very first case, when we check that mid element, start element, and the end element, right? The start, mid, and element are all 2's. Now here, our start and end ranges were dependent on those checks where mid is greater than start or mid is less than end or something like that. We would compare those checks and then we would increment or decrement our start position. We would increment or decrement our start or end ranges. Yeah, that was the case. But here what happens, that mid is greater is equals to the start is equals to the end. All three are same. Now if we come across such a situation, the program would fall into a loop. In that case, we can't do anything. We will be continuing in that loop forever. Out of bounds exception won't come. Time limit exceeded will come if you are doing Leetcode. So let's talk about this example. If we are stuck in that situation, let's say our array is of somehow the sticky note has come here. So if we come in such situation where this is our case and our start and end elements are same and we are checking mid, we will be comparing mid with those cases, right? Can we say that we can simply avoid this element and avoid this element because they are same with the mid element? Can we simply say that we can simply decrease the range of our array to, let's say we will not consider the first element and we will not consider our end element, with mid because all three are same. So if we don't consider them in our checks, then our array would become something like 5, 2 and 2. Yeah, it's still rotated, right? It's still a valid rotated array with duplicates. Yeah, and our target still lies inside that new array which we are checking after omitting the first and last index, because it was disturbing the conditions which we were going to put with the mid element. So we simply omitted them. That is our special case that needs to be done when we talk about duplicates, when the rotated arrays consist of duplicate elements. So that is our case. Now one thing, I am sure that many of you who are watching this, maybe now or maybe later, would have not considered this, that if we omit the first and last element, if they are same, first of all they need to be same, all three needs to be same, this condition needs to be valid, only then can we omit. But before omitting, did we even check that any of the start or end index was our pivot element? Because that could have been the case, right? That could have been the case. I'm not saying it is the case, but let's say something like phi 2 to phi. Yeah, if we are given something like this, this needs to be phi. So if we are given something like this where start, mid and end elements are all same, we are saying that we omit the first and last index. We will be taking only this. But here we can see that pivot element will be phi, this phi, not the other two phi's. Remember, if the pivot element itself has duplicates, then in the original order it would have been the last element in the duplicate. So if we write this in the original order, it would be something like 2, phi and phi, right? This phi would be coming to here. So we would be saying that this was the original pivot element, it just came here and the here, right? So if we are omitting this element, because we compared start, mid and end, all three are equal, so we omitted the first and last index. But here it's going to violate our condition that this phi was supposed to be our pivot element, and we just omitted it because all three were equal. So simply, before we increment the start index and the end index by 1, decrement in end index by 1, we can simply put a small check inside this, that if the start element is our index, means is our pivot element or not, right? Same goes for the end element, and we know that for start element to be the pivot element, the element after it needs to be lower than it, right? Yeah, so we can simply put a small check over here that if the start element is greater than the one after it, and if that is the case, then we return start element. And if that is not the case, if that doesn't reach this if block, the condition doesn't reach this if block, then we can simply increment the start operator, start pointer. Same goes for the end, and for the end to be the pivot element, the element before the end index an element that needs to be greater than the end element. So if n minus 1 is greater than n, then we simply return n minus 1. And if that is not the case, then we can decrement the end as well. So this is our special case. We can write the special case like this. These needs to be checked because like I explained, in some conditions like this, in this example, this is a prime example where the start, end and the mid elements all are same, but if we increment the start and decrement the end index, our pivot element could have been skipped, could have been omitted in that increment and decrement operations. So simply before we do that, we can put a small check if either of them are supposed to be the pivot point. If they are, then we can return it, right? So alright, so our first, our second, our special case are all checked. First and second are basically the same which we used for the simple rotated array, sorted array. We can simply put copy paste that into this one as well. For the special case, we need to apply it specially over here. Special check that if all three are equal, and if all three are equal, before omitting them, we need to check that if start or end could be the pivot. If they are, then we can simply return the start, the appropriate index from there. Alright, let's talk about third and fourth cases, because that's what was disturbing our actual logic in this. We can't actually use third and fourth one here, where we were actually checking the start with the mid and mid with the end basically. So let's talk about the third and fourth from here. Alright, so basically after these three checks, we can simply check whether where we are now. Means if some iterations have taken place inside the array, then we need to check that what is our current situation. We need to put some other checks as well, right? So we'll be doing that over here. So let's do that. Alright, so we can simply say that if the start element is less than the mid element, now we are checking start with mid, right? Or if start element is equals to the mid element, we need to put this special if case because of duplicates, only and only because of duplicates. And because we are also checking this case, we need to check the end element with the mid along with this, because both, if 1, 2 and 3 are given, means start, mid and end are given, and if 1 and 2 are equal, we check that 1 and 2 are equal, then we need to check 2 and 3 alongside 1 and 2 if 1 and 2 are equal. That is what we are doing here, right? So alongside this, we need to check that if mid element is greater than end element. Now this is our entire if case. What does this suggest? We are basically checking that we are checking that either of this is true, means first case, which is where the mid element is greater than the start element. You know that will only happen if mid element and start element both lie in the ascending case, means in the sorted part, right? If that is the case, then we know that some elements could be after it, right? There could be some elements that are after this mid element that needs to be greater. So let's say our duplicate sorted array could something be like 5, 5, 7, 2, 3, 3. This is our duplicate sorted array where start, end and 3. So this is our mid, right? Let me take one more element, then this becomes our mid element. So okay, so here we are basically checking that if mid element, which is 7, is greater than start element. If that is the case, then we know that we are in the ascending part. Means see, this is sorted part, this part is sorted and this part is sorted, right? That is the case over here. If this is true, then we know that something could be after the mid element. There could be some elements. We need to go further in this part. We need to check further in this part. Maybe there could be something that is after the 7th element. Maybe there could not be. We don't know that part yet, but we need to for sure check it if there is something after this 7. That's why we are basically checking this. Or other ways we could be checking. So what I am saying, that there could be something after that and we need to check. So that's why we are going start is equals to mid plus 1. That is the case for this one. Now in this case, if we increment the mid plus start, we update the start pointer by 1, then this would become our new start. 1, 2, 2, 3. This would become our mid. Now we know that this will completely violate our pivot point. but we don't need to worry because this is not our only check, right? The mid element checks were already given in the first and second, where the first element is where the mid element and the previous element is greater than it, then we simply return the previous. So that conditions are already checked. We don't need to do anything more about that. For this one, we need to update the start pointer, right? Same goes for this, where if not means if mid is not greater than it, but mid is in fact equal to the start, but mid is greater than end. What I am saying this over here, that if mid is greater than the end element, then that also means that end element is always going to be less than the start element in sorted array, in rotated sorted array, or anything, duplicates, non-duplicates. That is some common rule, that end element will always be less than the start element. That is the rule in the original one, right? So if this is the case, then end element is also less than the start. That also means that we are in the left part. Left part means the higher order of the sorted array, means in the greater part of the sorted part. So basically we do need to go forward to check. Alright, so that's why we are doing start is equals to mid plus 1, right? Also, I think we do need to apply those boundary checks over here. Maybe you can also apply, that is mid is less than start, means basically mid is less than no, I don't think we do need to apply. Where we do need to apply is in the mid element here, that if we do need to apply here start plus 1 or something, because we are checking the start elements, right? So if start is greater than 0 or something like that, right? So those boundary checks needs to be there every time. Alright, so if this is not the case where start needs to be updated, then we simply update the end pointer, where end is equals to mid minus 1, means we are in let me change the color. So if we are not in this part, then we'll be this part, we'll be in this part. We need to go backwards. That's simple common sense. Either we'll be in left part or we'll be in right part, right? We don't need to be in the right part unnecessarily. We need to cut down our mid and end index. We need to go to the leftwards, because when it's rotated, it will always be in the, means it will try to be on the left side generally, unless the mid element is our pivot element. Otherwise, common sense says that it will always be on the left side, because we are rotating it to the left. So higher elements are shifting towards the first indices. It will increment from the first indices. All the elements will be incrementing from the higher order on the first part. So basic common sense says that our pivot element tends to be on the left side. So yeah, let's code this. I'll write the code and show you the common logic as to how it sees. All right. Okay, so this is basically our main pivot code, where we are starting from the pivot element, where this first 4 cases, we are basically going to check the 4 main cases. First of all, we find the mid element. All right, the mid element is found here. Then we check the first 2 common cases that we always check for the start and end. All right, basically we find the mid element. Then we find then we check for the mid. The first 2 cases are for the mid, where the element after it and or the before it could be greater or less than it, right? So that one we already did it. Then this one's specifically for the duplicates, right? We check the duplicates, but before we increment the start or decrement the end, we both do simultaneously. We need to check if either of them could be our pivot elements. So we also do that, and we also make sure that our start is less than end, because that does not need to be violated, right? And for the opposite case, we need to check if end is greater than start, right? Because we are decrementing. All right. Then comes the third and fourth cases, right? That if we are in the left part, then we need to go further. If we are in the right part, then we need to go backward. All right. Let's submit it this. All right. Okay, it's good. In terms of space complexity, it's 50% good. In terms of time complexity, it beats 100%. So yeah, that's pretty good. All right, good one. I'll be talking about the next one. Next we'll be moving to the next solution, next problem. Alright, so I hope you understood the logic about this one. If in case any doubts, I appreciate your comments. I'll be reading them, so do make sure to comment it. Alright, so let's move on to the next problem. Okay, so let's get to the second question. So this one's about find the first and last position of element in the sorted array. Alright, so let's take the first example. We are given that 5, 7, 7, 8, 8 and 10, and the target is 8. So 8 and 8 are in the third and fourth index, right? So we'll be returning third and fourth index. That's common, right? Yeah. Alright, so if there is no target present, then we simply return -1 -1. If there is something present, then we return the index start position and the end position. Alright, okay, so let's understand how do we approach this question. Okay, so let's get to the whiteboard and we'll understand what implementation do we have to do. It's not that difficult. Basically it's simple binary search. We are still searching the target inside the range. So let's say our array could be something like 6, 7, 7, 8, 8, 10, and the target is our 8. Alright, so we know that when we take 0 indexing, because arrays always start from 0 when we talk about index. So 0, 1, 2, 3, 4 and 5. So we are basically returning 3 and 4 as our answer. So one thing that we are going to return for sure is the answer array, which will consist of 2 elements only, and they will always be full. Either they will be the actual range of index, the start and end position. The start position is the first and the end position is the last. Alright, so basically answer of 0 is our start position, and answer of first will be our end position. So when we talk about ranges, one thing that immediately should come inside our thought process and the way we approach it should be that what could be the brute force solution, what could be the at most anything. If you don't find out how to implement the answer, then in the worst case what can you do about it? So we can see that if we travel using linear search, so we'll come across this first 8. When we talk about linear search, it will be big O of n complexity, right? In terms of times, in space it's nothing because we are still using constant space. Okay, so we'll be recording this 8. If it is there, we'll be recording answer of 0 is equals I, because that I will be our iteration number. So basically we are storing that loop count for the first. Now the question arises that if we already come across the first index, then how do we store the second one? So it's simple. You can keep moving forward, moving forward and all, and we simply keep on moving forward till the actual target does not happen to be the next index. So here we know 8, then comes 8, so we'll still keep on updating our end index. So answer of 1 will be the new I, means maybe j or k, anything, and it will be updating till the target is not actually that answer, right? Or the more simpler way you can do is do a linear search from backwards, and the very first element you find out will be your last position. So if you start from right hand side, then the first 8 will be over here, which is our last index. And yeah, it's saying that the array is sorted, so there is no possibility that there will be something between these two 8s. If there will be, then it's going to be 8 only, because it's saying in the question that the array is sorted, so we don't even have to think. So basically do a linear search from left to right for start index. Alright, something seems to have stuck. Alright, okay, and do a linear search from right to left for end index. Those will give us the ranges. So what will be the time complexity? It's basically big O of n for this one, big O of n for this one, and we are basically adding both of these two. So it's going to be 2 of big O of n, and we know that in constants we are omitting the when we talk about complexities, we are omitting the constants. So we'll omit the 2, so it will still be big O of n, because we are basically traversing it 2 times till we find our start and end index. Now of course we are not going to do linear search, it's just the brute force approach that I gave to you. The thought process over here should be immediately that it's directly asking you to find the start and end ranges. It's giving you the implementation that the array is going to be sorted. What more to think when you are going to have to find something? Then it just apply binary search. So what our binary search would do in normal cases, let's say there wasn't any 8 here, alright. So what the binary search should be doing is it's going to give you the index, which is 3. It's going to return you the index in case of one element, right? We don't need to think about what the other duplicates are going to be in the array. We just need to care about what our target range should be. If it's just 1, then we simply return 3, 3, because the answer range is going to ask us 2 elements to give. So we'll be returning 3, 3, right? That's our start and end index, because it starts at 3 and it ends at 3. So we give 2 elements 3, 3, which are the indices. Alright, so how to implement this? So you know the very basic thing, when you don't know about how to change the main code about some algorithm, let's say binary search is our main algorithm, we also know that we are going to apply binary search, we just don't know how to change it a bit. So let's start by writing the binary search. We'll come across how to change, what to change, and where to change. Alright, so I'll make a function binary which will take in the array and the target. Now I'll also take a boolean value, which could be is first. I'll explain what the boolean value over here is going to do. So let's say the boolean value is true in the first case. We'll talk about that later. Let's start with the binary search. So our start is going to be 0, our end is going to be nums.length -1. Yeah, I hope we are used to the binary search algorithm by now. So start and end we got. So while our start is less than equals to end, we'll be performing the 3 cases. So the first one should be if our target, we should be finding the mid element first, which should be start plus end minus start by 2. Alright, so if our target is equals to the mid element, in that case we simply return the mid index. Alright, that was what we were doing in the earlier cases, right? Our main aim was to find the target element, which we always used to compare with the mid element, right? That was supposed to be how we do it. Alright, okay, so in that cases we used to compare the mid one first, but in here we'll be comparing that later. I'll just put a comment over here. This block we'll be talking about later. Let's take the consideration of the other 2 cases where we used to change our start or end pointers. So what about those? We would compare that if the target element is less than the end, is less than the mid, less or more, we would talk about those 2 cases, right? So if it's less, So we know that the target is less than the mid element. So we are going to search in the left part because target is already less. So we would decrement our end position. So end would become mid minus 1, right? That was our case. And if that was not the case, then we would talk about if target is greater than the mid element. Means we need to go further the mid, because something is greater and we need to find the target after the mid. So we would update our start pointer. So start is equals to mid plus 1. That's what we have been doing for the shift, updating the start and end pointers. In the third case, we would compare that what if our mid was the target, right? Then we would simply return the mid index. Now here we can't simply return the mid index. We need to take in consideration that what if there is something before or after that mid index. So here let's take a new fresh case of example. So let's say 6, 7, 7, 7, 8 and 10, and our target would be 7. Target would be 7. So somehow, some way, if mid would come to this 7, we can't simply return this mid, and we also can't consider this 7 as our first or last position either, because it can't be our first position. The first position applies to this 7. This is our first position and this is our last position for that range. So if we somehow come to this 7, we can't simply return it. We need to check if there is something other before this element that is equals to this element, which is our target, and if it is, then we need to update that to our range, right? We need to keep checking backwards. Similar case for the forward case, that what if something is after this target element, which also happens to be our target element, then we need to keep checking forward till there is nothing to keep checking forward. Means till our target element is not present after the element. So here we know that if we somehow come to this, then we need to check forward if we are checking forward, right? So we come to this one. This is still our last index. When we talk about last index, we need to keep checking forward. So we know that we again found our target, so we need to keep checking forward. So we come over here. Now this is not our target, right? So we need to stop over here. We need to return this as our last index. Same goes for the other case. If we are here, then we need to go back. We need to check if the previous element is equals to our target. If it is, then we again need to go back to check if it is again going backward or not, if the range is longer in the back side or not. So here we know that 6 is not equal to 7. So we need to stop over here. We need to return this as our start index. So this is how we return our start index and our end index. The range, we need to do this for both cases when we talk about the first position or the last. So for that, going backwards, let's make a variable int answer, not our main answer array. Let's make a variable int a is equals to -1. For now, we will initialize it to -1. Alright, so here we got to else if. Alright, so if else if, and then we go to else, where we should be checking our mid case. So here we should be checking that first of all, what should we check? Should we check the first position or the last position? So that's where our is first variable comes in handy. So when this is very convenient for us when we call the binary function, because we need to call it 2 times, one for the start and one for the end. So when we call for the start, we can simply say that is first is true, and when we call for end, is first is false. All right, so let's see how that logic works. So else, let's first, before we check whether our answer, where we want to check backwards or forwards, let's first declare our answer, that a variable, as our mid, because we actually stumbled to a case where our mid could be our target element, right? So we will just store that a over here. All right. So now we will check if is first is true or not. Basically this is first is a boolean value. So if it is true, so we'll be checking our first half. So there we will be decrementing. So end is equals to mid minus 1, and if that is not the case, then we need to check the other case where is first is not true, means we are checking the last position, last index. So there we will be updating our start index is equals to mid plus 1. Very convenient. So what this block of code does is that first of all it takes in the mid value, it stores the mid value in that a. Now that a could be anything, right? It just takes in the mid value. If there is no mid value to be checked, whether it's a target. Oh, one more thing, we can't simply take in the mid value, we do need to check if that variable, if mid is equals to the target, then only we do that, then only we take in the answer and then only we move ahead. All right, if that is not the case, then we simply keep it to -1, and in the end we will be returning the a, because a could be -1 or the actual start or the end position or the last position basically of that range of our target. So basically what this a is going to be when we call it twice, let's take a example that we will be calling binary on our nums, our target, and true. The same binary will be called again for nums, target, and false. All right, and we'll be storing that in first index and the last index. So when we say true, it will go backward to check whether anything more to check for the first index, and when we say false, it will go ahead to check whether there is still something more in the target to check or not. All right, so let's see how this works in the code. I'll write the code and then explain you in more depth. Okay, so this is our code, and I think we don't need to check whether our answer is equals to the mid over here or not. We simply declare the mid as our answer. I just took answer as -1, and we don't need to even check whether our answer is equal to the -1 or whether the mid is equal to the target. Even if it's not, it still needs to take in the mid value for the answer, right? And in the end we will be returning the answer, right? And in the very actual function we'll be calling it 2 times. First one where we'll be declaring the is first as true, means the first start index as true, and for the second case we'll be calling it as false. All right, so let's submit this one. And yeah, it beats 100% complexity. All right, so this was for the second example. We'll be moving with the third one. Okay, so let's talk about the third one, where we are asked to find the single element in the sorted array. So we are basically given an array of which contains all the elements in 2, means all the elements are repeated once at least, except for one element, and we are going to return that element. So in this first example, we are given 1, 1, 2, 3, 3, 4, 4, 8, 8. So we are returning 2 because 2 is not repeated. So and we are asked to do it in O of log n. So immediately you should be thinking that it's saying that the array is sorted in the very question. It's saying that single element in a sorted array. So and we are asked to do it in O of log n. So immediately it should be striking that we are using the binary search over here. All right, so let's see what to do and how to do. All right, so we are given the array. Let's take an example of this array. So I'll create an array of 4, 4, 6, 8, 8, and 10, 10. What we should be returning, let's increase our array actually, because maybe this will help us more in understanding. 1, 2, 1. All right, so what we should be returning is this 6. We should be returning the 6th. All right, so it's asking us to do binary search. All right, so we'll be doing binary search. Okay, so it's sorted, right? We'll be simply if we can't simply apply binary search over here because we are taking in consideration of duplicates. See, literally every element is duplicated except for one. All right, let's talk about the indices of all these elements. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So there are 11 elements, right? N is 11, 4, 6, yeah, N is 11, and the last index is 10. All right, so if we somehow happen to find the pattern as to what is actually happening, only then can we implement that pattern inside our binary search. So without that, I don't think we can, because it's asking us not to create any extra space. It's saying that do it in O of log and time complexity, and do it in O of 1 space complexity, means constant space. Don't use extra space, just return the answer. And it's also saying that there will be returning something, means you have to return something, either return the actual single element or don't return it and simply return -1. All right, so let's get to the implementation. Basically it's very easy. If you somehow are able to find the pattern inside this I created, so if you somehow find the pattern as to what is happening over here, then it will be very easy. And then it's basically simple binary search. That's why I even wrote the indexes over here. So you can see that 6 is the answer which you are going to return, and 6 is also the index. Index is 6. Yeah. Let's talk about the somehow it's coincidental. I didn't mean to make 6 as the index for the answer 6. So let's talk about the indexes of the pairs. Let's talk about that. So 1 and 1. So they are 0 and 1, right? 2 and 2, there will be 2 and 3. 4 and 4, there will be 4 and 5. We'll skip the 6th one. Then 8, 8 are 7 and 8. Then 10, 10. They are 9, 10. Yeah. 0 and 1. So where is the partitioning happening? So after 4 and 4, the single most element is coming, then 8 and 8. So let's partition all our pairs from there, here. All right. Now let's talk about the indexes, all the indices before the actual single element. So we are given 0, 1, 2, 3, 4, 5, and this is left. Okay, so this is left, this is right, something has, okay, all right, so this is left, this is right, this is left, this is right, this is left, and this is right. All right, so for left and right, can you somehow find a pattern for the indexes? Let's not talk about the actual elements, I'm talking about the indices. For 0 and 1, 2 and 3, 4 and 5 for left and right. Yeah, so I simply just classified into a more watchable manner. 0, 2 and 4, 1, 3 and 5. 0, 2 and 4 for left. Can you see that all these are even? And for right, 1, 3 and 5. Can you see that all these are odd? Yeah. See, that's our pattern. Let's do the same for the indices after the single element. We'll make the same table, left and right, left and right. We'll not take in consideration for the actual elements, but we are just talking about the indices. So 7 and 8, left for 7, 8 for right, 9 for left, and 10 for right. Yeah. Can you see all the elements in the left after the single element are odd, and all the elements after the right, all the elements after the single element for the right are even. So basically the parity is shifting after the single element. This is our pattern. So when we talk about binary search into this consideration, we are talking about three cases. The two cases are, out of those three, the two are to shift the start and end pointers, and the third case, which is the main, which we are returning the mid. If we find the mid is equals to the target, then we return that mid index, right? That's what we are doing. So let's talk about those three cases in comparison with this. So here that single element could be our mid case, that if single somehow matches our condition, then that will be our returning element. Basically we are asked to return the element, not the index, or maybe the element. Yeah, we are asked to return the element. Okay, so that element, that single element is our mid when we compare that binary search with this example. The other two cases are about left and right basically. So if we somehow spot that, let's talk about left or right, we can't take both into consideration because we'll work with either. We can work with right over here and the right over here as even, or we can talk about left and left. We can't take left and right both into consideration. So we'll be going with right. Let's do it with right. We can also code in left. I'll explain that part later. All right. Okay, so let's talk about the right one. So right is odd when single element has not come yet. All the indices are odd in repeating numbers, right? We are talking about repeating numbers, and all the elements after the single, all the elements in that pairs of duplicates in single after the single are going to be even. So odd shifts to even. Yeah, so basically we take right into all the right elements, all the second elements in the pair. Basically we take those into consideration. We keep checking whether if it's odd or not. So basically if it's odd, then we know what to do. We need to go further, right? Because the single element is going to be after that. So we keep going forward. So basically our start is equals to mid plus 1. Yeah, now you can spot the pattern, right? And if somehow the right element which we come across happens to be the even, then we know that we need to go backwards. So our even would be backwards. So basically our AND is going to be backwards. So let's write the pseudocode and it will become clearer. So let's go with while start is equals to less than end, while start is less than end. Basically our mid is equals to start plus end by 2. That's very common by now. Let's talk about either of the cases. I'll still talk about either. We can take either left or right. We did with right. Right is going to be odd before the single element appears. It will be even. For left it will be even before the single. It will be odd after the single. So we'll take either. So if mid, whatever element which we find every time which is mid, if that somehow happens to be odd element, right, is equals to mid mod 2 is equals to 1, means it's somehow leaving a reminder. We are talking about the indices, not the element. I hope the pseudocode makes it clear. This is the index, not the element. We are only comparing the index. All right. So if mid mod 2 is equals to 1, means this is the odd element in the pair, right? That's what we are talking about. Mid mod 2 is equals to so we do mid minus minus. Now basically what I did right now is, by decrementing it by 1, I simply made it an even case. I simply made it even. All right. Yeah. Okay. So I made it even. Yeah. Alright, so what is even? Even could be for left, it could be in the left side, and for odd, it will be odd after the single element. Yeah, so we are taking the left one right now into consideration. Now we check that if the mid element, now we are taking the element actually, not the index, which is equals to the mid plus 1. So the left one and the right one, basically the first and second. This is the first, I am just making it clearer. First element in pair. Yeah. So if both are equal, first of all, then what do we have to do? So if both are equal, and I just made it even, right? So the left one should be even. Now when left is even, let's come to the table. We are saying that left is even, the left element in duplicate is even when the single element has not appeared yet. So if it is even, then we need to go further to check, right? So what we would do is start is equals to mid plus 1. That is what we are doing in case of binary, but this is binary with all duplicates present. So if we do plus 1, then we will land to this element. Can you see that we are in this element right now, and we are checking that if it is equal to the next element, means if we are basically validating that is this a duplicate, is this the pair of that duplicate. If yes, then we don't need to have to increment it by 1, because if we increment it by 1, then we will be landing to this case. So no, we will be incrementing it by 2 for this case. This is the specific implementation case. All right. So start is equals to mid plus 2. Yeah. All right. So if that is not the case, means if these two are not equal, when would that be occurring? So basically this else basically says that if mid element, not the index, the element is not equal to the mid plus 1 element. So if that is the case, meaning this mid is the second element in the pair. Second element in the pair, right? That's what I'm saying, means the actual pair is supposed to be behind this mid, means the actual pair would be something like mid comma mid minus 1. That should be the pair, means basically I am taking mid minus 1 after this, but we should be taking it as mid minus 1 and mid. I hope you are able to understand what this else block basically is considering the logic as, right? So if this is equal, let's talk about this one. If this is equal, means the element and the one after it is equal, means the left one is supposed to be the even, right? I made it the even case. So left is even, and if that is not the case, means the previous element is part of this pair, means the previous element is supposed to be the odd one, because I made the mid as even, right? I made the mid as even. I'm just taking the even cases for mid. So if that is not the case, then the previous element is the left one, and the previous element should be odd in terms of sense. Yeah, and when left is odd when it appears after the single element. So we need to go backwards, but we can't simply do the same logic as start is equals to mid plus 2, so end should be mid minus 2. We can't do that, because there could be some element. What if we do end is equals to mid minus 2, but what if the actual single element could be mid minus 1 or even the mid? Yeah, that could be the case, right? We can't directly skip backwards two elements. We need to check these two. So simply in else block we need to do end is equals to mid. So that will make sure that those two elements which we want to skip are not skipped and will be taken into consideration. So I hope you understood this logic block, because it's very simple. I made it clearer as well. Alright, so in the end, now what will happen in the end? The main base case is while start is equals to end, but if you dry run this thing, then in the end our start will be equal to the end. That will be the case every time, and this start is equals to end is our single element, because it will in the end stumble, it will keep on shrinking and it will reach to a one single common case, which is the element which does not have any pairs, and it will be the case which we will returning. So we will be returning either nums of start, or maybe we can also return the nums of end. Basically mid, start and end will all be equal. That's what I am trying to say. We can also return the mid, because end is equals to mid, all three will be equal basically. But we can't return the mid because it is inside the while block, so we can't return that. We will be returning the start or the end. Alright, so I hope that made sense. I'll write the code and then we'll see what I did inside the code, right? Okay, so this is our main case where we simply initialize the start and end. We make a simple while loop. We declare our mid, which is still all binary search till now. We are now checking that if mid mod 2 is equals to the 1, means basically if it's the odd element, then we make it even. We make this case even. We want to only consider the even cases, right? Even case. Now we'll be checking if this mid is our left element or the right element. Means if it's whether it's the left part of the duplicate or the right part of the duplicate, right? That's what we are checking. If it's the left one, then we know that we are in the left case, means we need to go further, right? So start is equals to mid plus 2. I explained that part in the board. And if that is not the case, means we are ahead of the single element, we need to go backwards, but we can't decrement it by 2. We need to consider those two cases which we are going to which we want to decrement. We can't decrement, so we are all simply making it as mid, and in the end we can return start or end, either case will work, and we can simply submit. That will be our single element. It will return us the single element. Yeah, it beats the complexity and all 100%. It's good. Space complexity is yeah, I guess it's good as well. Alright, so I hope all these three codes helped you develop enough logic for binary search. The next few examples I'll be talking about will be about sorting, mainly related to cyclic sort and all. If you understood this video till now, then trust me, the sorting videos, the sorting implementations will be much easier, right? Till we come to the till we reach the merge sort and quick sort, right? Because we haven't discussed about recursion yet. We'll be talking about that very soon. I am excited to teach you about recursion. So I hope you are following the DSA playlist till now, and yeah, keep practicing. I'll also upload the code in I'll also upload all the code files inside the description boxes in all the previous videos as well, so you can follow through all my codes in the Leetcode or maybe my GitHub repository. Alright, so make sure you like and subscribe to the video, and yeah, thank you. Alright.